The presentation in 30 minutes allocated to us, so we're going to be talking at speed of Cassandra. But if you have any other questions, feel free to come by the experts room and ask anything that you need. So my name is Ameet Chaubal, and with me I have my colleague Fausto. And we're from Accenture. I'm from the big data group within Accenture, and Fausto works for a little cooler group within Accenture called the Labs, where they do R&D stuff on new technology. We're going to be talking about an evolution of how do we solve a very typical problem that is encountered in many organizations, which is about ingestion and analysis of large amount of data. And we're going to walk through how the problem was solved in the olden days, how we solved it for a particular client, particular use case, and what sort of opportunities are available for solving it in future, especially with the advent of some of the newer technology that has come around. So that's the flow through which we're going to walk through. First of all, the problem, which was for a financial organization, the typical problem space consisted of ingesting high volume of data, which was coming from an internet or e-commerce transaction website. The objective was to accept the data, store it in some sort of data repository, perform analysis in order to answer questions, and help customer service calls within a very short window, and then eventually get the data out into a data warehouse where it could be married with other parts of the organization, other data coming from different parts of the enterprise, and then perform BI-related queries. So this is a very typical use case. How have people been solving something like that? So you have your standard, some sort of a website-related data which is generating your transactions or messages for your application. And in order to store the data in some sort of a database, people have been inserting a JMS queuing system in the middle, which would allow you to decouple the front user-facing website from the back-end transient data storage system. And that just allows you to scale your infrastructure in a more balanced fashion. And then eventually you can get the information out into whatever analytical format you want. Some details about our specific use case. So we were dealing with about 5,000 messages or transactions coming in per second, and the transaction size was around 1 KB for each message. And this was for a very large organization, so throughout the day the messages were coming in. So we might get into 200, 250, 300 million messages of 1 kilobyte in a day's time. Obviously, we had the queuing system, and then the data storage for transient storage was done in an Informix traditional database. And eventually, the data was extracted into a massive data warehouse hosted using Teradata. Just to add some more color to it, so what was the problem with it? The main problem was around the transient storage. Obviously, it was over a period of time not able to keep up with the volume that we were talking about. Now, that problem percolated downstream and reverberated upstream as well because of the failure of the system to keep up with the incoming data. That translated into loss of messages in the queuing system. The queuing replication was an issue. The other thing was that the sort of messages that were captured, which were supposed to give us the ability to ask questions and solve customer problems, it was difficult to do those things at the same time as ingesting the data. So keeping up with the read and writes was becoming a challenging thing as well. And the data extraction was done in batches. So every 4 hours, we would extract the data, load it into Teradata data warehouse. So eventually, by the time the whole process finished, you might have a delay of up to 24 hours. So the data warehouse was always lagging in terms of what the information that was being ingested. The additional thing was that there was no low latency type of application that was available because the system, the transient storage itself, was not able to keep up with its main functionality. So any other applications such as low latency or dashboard sort of applications were pretty far out in future. So just to recap the problems, high rate of ingestion, ability to keep up with incoming data, no low latency dashboard sort of application, and also we didn't have any way of doing pattern detection on the incoming data while we were ingesting it in order to make some sort of decisions or trigger any alerts. So what do we do is, as I said in the beginning, the first thing that we did was replace the transient storage with Cassandra because of all its features in terms of high ingestion capability. So rest of the pieces stayed pretty much the same. The messages were ingested, put on the JMS queue, and then using Hector client APIs, we ingested the information into a Cassandra cluster. The other thing was that since we were using DataStax's version of Cassandra, it allowed us to have Hadoop integrated into Cassandra, which meant that without doing any sort of ETL, now we had the ability to not only ingest the data, perform low latency queries, but at the same time have the same data available via Cassandra FS for doing MapReduce applications or just simple Hive queries. And all that while the data was being, as soon as the data landed, it was made available for Hive queries. So what is the role of data model in all this process? So before we go into what exactly the data model was, I want to just segue into what are some of the things that are missing in Cassandra when we compare it with a traditional RDBMS and go from there. So I don't really want to say these are shortcomings, but actually, there are opportunities for us to transform the way we have been dealing with the databases in order to avail of new features that are available in systems such as Cassandra. So it might take a slight change in our attitude. Rather than saying that this is how I've been doing things in Teradata, show me how I do it in Cassandra. Well, we would slightly change the question and say, I'm going to forget how I've been doing things with Oracle and Teradata and see what the features and capabilities in Cassandra are, and then tune myself and my business and my way of doing things so that it better molds itself with what Cassandra offers. So obviously there are no joins, there are no ways of doing aggregation queries, and with random partitioner, we're not able to organize the keys in a certain order. So if we look at them as opportunities, that'll give us the impetus to structure our data model according to certain features that are available. So what are, before we get into the features, in order to get around those lack of features, we have to do smart denormalization because we don't have joins. We have to use client or application along with the database. We're all used to doing analytical queries in Oracle with windowing functions and lead lag and regression and what have you. So in this, when you switch gears and you're in Cassandra, you're going to have to leverage the application. So together, the application and the database will give you the entire solution. So that's the way that's the lens through which I would look at this problem space. So what are some of the features of Cassandra modeling that are really, really useful that we utilize? Well, first thing is having the ability to organize the columns or organize your data in a wide format rather than in a vertical format. This allows us to change the way we've been storing the data in a vertical way in a relational system into a horizontal fashion. The other thing is that all the data that is stored horizontally is stored for a certain key, is stored on a single server. That also gives us the ability to access it very, very quickly in order to perform any sort of calculations, any sort of analysis on all the records pertaining to that key. The other thing is that, which is very different from a traditional database, the name of a column is of great importance with this system, which means that we are able to store actual important, useful information embedded as part of the name of the column. Whereas in a traditional database, all we could say was social security or first name or last name equal to this, greater than this, but we couldn't store important information in that. So that feature is of great value, and we ought to use it to our fullest advantage. And the last thing is having composite column names, so that in addition to having information in the names of the columns, we can group such entities together into a composite so that what entity gets formed gives us a lot more capability to store the data in just one single column name entity. So together, the name of the column, which could be a singular or a composite entity, and the value of the column give us a very powerful structure in order to store the data. So in this case, how we stored the data. The other thing about storage of data is what is the primary key or the row key for which you are storing the information. This becomes extremely important because of the wide structure of your data organization. One advantage or one ramification of storing the data in a horizontal fashion is that you are automatically getting a group by or a bucketing effect. So whatever is your row key, you are essentially collecting all the records or all the columns for that key, or Cassandra is doing that for you. So it's important to choose the granularity of that key so that you get appropriate number of records bucketed for you. For example, if I am collecting messages, let's say, which are coming in every second, then in a second time, or in a minute, I'm going to have 300,000 events. If my row key had a minute value, then all the messages coming in that minute are going to go horizontally in that single key. And if you have a 1,000-node cluster, or whatever, 100-node cluster, all the 99 machines would be sitting idle, not doing anything, except the one machine which got that key allocated to it via hash. So you have to be careful how you construct the key. So in this case, in order to remove such hotspotting, as well as making sure that everyone gets a chance to play, we used a notion of partitioning, which is essentially making the primary key a composite structure so that automatically a given minute data is divided across a certain number of row keys, which can be spread across all the machines in your cluster. The other thing we used was composite columns. So in composite columns, one way to do that would be when you are structuring this composite entity, it would be wiser to structure the columns in such a way that the granularity of these columns goes on increasing. So that means the first column name or first piece that you're using to construct your composite entity contains a lot of rows. Then you go narrow down. So essentially, you're drilling down from the first one all the way to the end, which would allow you to construct where slice predicates or actually do queries against this data in a more meaningful fashion. The other thing is that all this data stored in a horizontal fashion is automatically sorted by Cassandra. So you can take advantage of that in constructing this so that you are able to do a proper arrangement of records when you're retrieving them, when you're storing them, when you're querying them. And that's one of the great features that the system of horizontal ordering allows you to have. Benefits, of course, we have geo-redundancy that we were able to do in this case. Data consolidation, we had a single view of the data as opposed to two different data centers. And we were able to do low latency application because we can perform queries or reads against the data. What are some of the opportunities remaining? There are real-time pattern detection, and such sort of things come about because of the advent of some new technology that has come on the horizon. So we will take it from there to see how the next iteration of an architecture like this could be done. And for that, I'll turn it over to Fausto.
So Ameet talked about what to do when you have an existing system that you need to bring up to date. What happens when you have a greenfield opportunity where you're trying to create a new product from an emerging technology, from emerging technologies? So what I'll talk about today is the Accenture Cloud Platform. And what the Accenture Cloud Platform is a cloud brokerage that allows us to provide our assets to our clients in an on-demand, elastic manner. On top of that, we've built big data capabilities to handle different classes of big data workloads. The first iteration of this was batch-oriented. So it was essentially doing collaborative filtering as a service to provide targeted product recommendations. The current iteration is based on stream processing, and this is what I'm going to talk about today, and event detection. And the first use case for this was network analytics. So why network analytics? Well, if you think about service providers, they're kind of in a grim position right now in terms of network loads. Obviously, we know there's been a proliferation of consumer devices, tablets, smartphones, set-top boxes, whatever have you, and most of the increase in that data has been in video. So what does this do? It puts tremendous load on the network. This, in turn, causes operational costs to go up. It makes understanding defects within the network more difficult, and it affects capacity planning. And all of this, in turn, makes it influences the end user experience very directly. If you can imagine, if you can't understand why a defect is happening, you have slow network speeds, you have buffering events. If your video is being slow when you're trying to watch Game of Thrones on your iPad and you can't find out who's getting their head chopped off this week, you're going to be angry. You're going to move to the other service provider, right? So it affects customer churn. So really it affects the bottom line of our clients. So how do we go about understanding what's going on in the system? And the example I'm going to be talking about today is specifically suboptimal events. So suboptimal network speeds. In this use case, we're talking about web logs, essentially, or logs as a whole. So in order to do that, we're ingesting into a distributed queue, in this case being Apache Kafka. We're doing pre-processing in Storm, and eventually it ends up in Cassandra, so our distributed data store. As Ameet mentioned, because the data stacks allows you to integrate with Hadoop, which gives us access to the entire Hadoop ecosystem, which allows us to use things like custom MapReduce jobs, Hive, Pig, to understand what the correlations are and what is actually causing those suboptimal speeds. So is it based on devices that people are using? Is it based on the browsers that people are using? Is it based on location? Are all users from a certain region having slow speeds? Once we know that, and once we understand what those scoring metrics are, what those patterns are, we can then implement them back into Storm so that next time you have those messages, those requests coming through, you can understand what's happening and raise events based on that. In the simplest use case, we're writing to a specific column family for further analysis, but you can see how this can be, events can be raised to external systems, other systems internally, to clients, to end user UIs. And finally, we visualize both from the data store and from the real-time event notifications using things like D3 and cross-filter. And as you can see, the pattern itself is very iterative. You take what you know what has come in already, you do analyze that, and you feed that back into the system, so next time you can respond to that accordingly. So I can, have a whole presentation on any one of those components. The one we're going to dive in today to understand how it works with Cassandra is Storm. And so the question is, why use Storm for stream processing? Well, first is looking, like any technical system, you understand what do I need from this? Well, like as I was saying earlier, we're really looking to build a platform that can handle multiple use cases. So we need to be able to do several things. Do processing, aggregations, joins, complex computations. And we need to be able to have a system that allows us, or a framework or tool set that allows us to build for all of those and gives us the flexibility to build for all of that. We are looking at heterogeneous data types, at requests of different sizes, a data of different sizes, and of different velocities. And as I mentioned earlier, that is scaling up continuously. So we need something that can function well now and in the future. So we need a system that can scale accordingly. As I mentioned earlier, it's mission-critical data that needs to be fault-tolerant. And I would posit that when you're doing time series analysis and pattern analysis, two things become vital: understanding the atomic events that occur and understanding the sequence in which they occur. So we need to be reliable both in the ordering guarantees and in the processing guarantees. So how do we get this from Storm? The different use cases we get from having low-level primitives that allow us to build those. So I'll get into this a little bit further, but having what essentially is plain old Java code that's encapsulated in certain classes that implement certain interfaces allows you to be very modular in how you build these, and allows you to think about your analytical workflows as a catalog that you're composing together to do what you need it to do. Secondly, scalability is provided through a multi-tier parallelization strategy where you can go down to the level of those the specific primitives and choose how those are going to be parallelized. And you can imagine if you're doing more complex things, more complex computations versus doing something maybe simple like parsing a string, you're going to need essentially give that complex computation more juice, and it allows you to do that. The fault tolerance is gained through robust failover strategies, and reliability through tunable processing guarantees. To understand what the pyramids I talked about, and some of you might be familiar with Storm, some of you might not. To give you a high-level overview of the concepts, the topology is really your streaming processing application. It's analogous to a MapReduce job, except MapReduce job finishes. Well, this lasts forever until you kill it. How we break it down for this type of analysis, it's based on the analysis that you're doing. So suboptimal network speed will be one topology, geospatial analysis would be another. You can do those simultaneously, but again, since we're trying to build a platform, we need to be portable across different clients, across different projects, so we need that level of portability. The stream is what actually carries your data throughout the topology. And streams are made up of tuples, which are developer-defined schemas of data. In our case, it's the request information. So things like IP, the referrer, the user agent, the timestamps make up each of those tuples. The spout is what takes the data from the external source and emits it into the topology. So in our case, it's a distributed queue in Kafka, but it could be APIs, it could be other databases. Finally, a bolt is what's actually doing the processing. A bolt takes a tuple, does some processing on it, and emits it to the next one. Again, it helps to break down everything to kind of its lowest level of processing. So for us, it's things like sessionization, speed calculations, parsing, and again, it helps you think of things in a very modular way to be able to think of these processing workflows as being a catalog that you can compose together. So integration with Cassandra, why does this work well with Cassandra? Well, if you think about everything that I just talked about scalability, about having high throughput parallelization, all of that complements very well with what Cassandra can do. It doesn't help us if Storm can process thousands upon thousands of messages a second if the database can't handle those writes at the back end, right? So we need something that can work well together with that. What we did, we built a custom bolt because we needed dynamic columns per request to be written. I would urge you to not do that and use the available things that are out there. There's a great community around Storm that has built a lot of custom classes, especially for Cassandra. So I would go out and look for those. And finally, quickly, because I have to wrap up, we're going to run through an example of how we actually do this. This is a simple topology showing how we pull from the Kafka spout based on the IP. We group based on the IP address, so this is for a specific user. We do some pre-processing, some parsing, create the session, understand what a session is. This is arbitrary, right? This can be something that you define as a pattern or something that you create as a time window that you define arbitrary. But the nice thing here is that if that strategy changes, you can plug it in and out of the topology. That's the power that it gives you. We calculate the speed per the session. We keep a running tally of all this average speed for all the sessions and understand if the current session is suboptimal. Once we do that, we store that into Cassandra. What you can do with Storm is it enables parallelism. So you can guarantee that all the messages for specific user, for specific IP address will be processed by the same instances of those bolt objects. And obviously, this helps with throughput, but it also guarantees that. And again, it helps that Cassandra can handle this kind of write loads from multiple threads. And finally, branching and joins. So as you can see here, the top stream is doing what we just talked about, but the bottom one is actually finding the average speed per the location, and per location across all users. So we can compare that user speed to the speed of all the other users within that region and compare those. And I think I am out of time. And then these are some lessons learned I can go into. Again, as Ameet mentioned, come talk to us. Kind of out of time here, but come talk to us at the Experts Lounge, and we're happy to talk to you. Either me or Ameet, my team is here. Sonali, Mike, Anil, everybody raise your hands. They'll be happy to answer questions. Yeah. So with that, thank you.
Yeah, and thank you.